All right, so we're back, and if you'll kind of recall from the last video, what we're going to do is look at the relationship between runs scored by a team and the team's batting average, which is just the number of hits divided by the number of at-bats for that team. Then in the handout that you'll do on your own, you'll compare what we find here to the relationship between runs scored and this newer baseball stat, this on-base slugging statistic, which is supposed to be a better predictor of the number of runs that a team scores. And so we're gonna kind of frame our model a little bit theoretically here by writing that our response is going to be some function of an explanatory variable plus some model error. In simple linear regression, this function has a very particular form. And so, in particular, this function of x is going to be some constant term that doesn't have x in it, which is the intercept, plus the slope times that predictor x, and then we're adding in the error at the end, just like we did before. And so just to define some of these things on the side so we're all super clear, this beta naught or beta 0 is the population intercept. And so it's a parameter of our model. Beta 1 is also a parameter, and that's our population slope. X is our predictor. And then our error epsilon, we're assuming is normally distributed with mean 0 and standard deviation sigma with a little sub epsilon. Okay, so for now, we're mostly gonna ignore this epsilon error term. And so we'll talk about it in, still in this note packet, but in kind of the next section, we'll talk more about the errors, and then we'll talk about the assumptions on those errors. But for now, we're really gonna focus on this kind of slope and intercept part. And so if y is completely unrelated to x, we could also consider just a constant model, which would just have the form something like this. And so notice here that there's no x, and so it's just a mean or an intercept plus the error. Just to connect it to what we did in the last section, that model is really the same as writing the responses, the mean plus the error term. If you just let beta naught equal mu, then they're the same exact model. So really this is the model that we did in section 0. All right, and so let's tie kind of some parts of that model into our particular example that we're working with this baseball data. And so given this research question, our response variable y is just going to be the number of runs. The explanatory variable x in this example is the batting average. And so the graphic that we used in Introstat to look at the quantitative response versus quantitative predictor was a scatter plot. And so we're putting our response on the y-axis, our explanatory on the x-axis. And this is probably review for most, if not all of you. And so you could describe the relationship between these two variables. As long as there's no curvature, which it really doesn't look like there is, then we could say that this relationship is linear. So we're saying that because there's no curvature. We could say that the relationship is positive because if we kind of drew a fitted line through these points, it would be sloping upward. A negative relationship would have a fitted line sloping downward. And then strong or weak, I'm going to kind of go middle of the road and say that it looks like this relationship is kind of moderate. And so it would be strong if you drew a line and all the points were really kind of tightly clustered around that line. And it would be weak if the points were kind of a lot, or were kind of scattered around that line a lot. And so this looks like it's somewhere kind of in between those two extremes. All right, so rewriting the model from the previous page, we're just going to write it in terms of our example now. So like we set up here, y is the number of runs, x is the batting average, and that's in a percent. And now what we need to do is find some estimates for beta naught and beta 1. And so since they're parameters, like we said before, they're usually unknown and a little bit kind of theoretical. But what we need to do is use the data that we actually observed up here to find some estimates for these two things so that we kind of have this fitted model that we could use maybe to maybe in prediction or use in some inference about this slope parameter. And so we'll talk a little bit about how to find the best possible estimates for these two things in the next video.